All right, we'll take a look at some general periodic trends today for 7.12. We have 4 main periodic trends, and only 3 of these are actually in Chapter 7. The 3 in Chapter 7 are atomic and ionic size, how big an atom and an ion are, ionization energy, the energy required to remove an electron affinity, the energy that we need to put an electron on to an atom. And then the 4th, electronegativity, is actually more brought up in Chapter 8, but we will discuss it briefly in this video. Here's a main point we need to understand, that higher effective nuclear charge electrons are held more tightly. Okay, so if you have higher nuclear charge, so you have more protons in that nucleus, those protons are going to act to hold on to those electrons more tightly. And we should understand that. It's like putting more magnets into the nucleus, and those magnets are going to really attract those electrons. Another thing, larger orbitals. So if we look at the periodic table and we kind of go down the periodic table towards the franciums and the tungstens and the leads, the things in the bottom of the table, those elements have larger orbitals. And those elements have electrons that are held less tightly. And the reason is because there's a shielding effect. Okay, there's a shielding effect that shields the outer electrons from the nucleus. And so it's easier to pluck those electrons off of the atom. So we see this type of trend on the periodic table kind of reproduce itself quite often, where you have a decrease in the energy that's needed to remove the electrons as you go from top to bottom, and an increase in the energy needed to remove the electrons as you go from left to right. Okay, so we'll explain that a little bit more in detail. Let's look at the first periodic trend that's kind of important to us. It's called atomic radius, so the size of the atom. In general, as we go across a period from left to right, the atomic radius actually decreases. And that's kind of weird. We think of those atoms getting bigger. Well, they're getting bigger as far as mass is concerned, but their overall radius actually decreases. And here's why. The nuclear charge increases. More protons are being placed into the nucleus. Therefore, the valence electrons are drawn closer to the nucleus. Again, we're putting more magnets into the center. This then decreases the size of the atom. So there's a couple of key buzzwords here that you kind of should be aware of when you are talking about this concept. Let me get a highlighter out here. There we go. Okay, so what are we looking for? Effective nuclear charge increases. So the nuclear charge increases. Therefore, the valence electrons are drawn closer. So valence electrons are closer to the nucleus, so that decreases the size of the atom. All right? All right, in general, as we go from top to bottom, atomic radius increases. And that is, I guess, more common sense. You know, again, the atomic number is going to increase as you go from top to bottom, so, you know, you would think that the size of the atom would increase. And that's true for this case. Well, why is it? Well, simply because the orbital sizes increase in successive principal quantum levels, or successive energy levels. You know, you're getting larger s orbitals, you're getting larger p orbitals that are being placed into your atom. So those electrons thus are getting further and further away. All right, so here's the two things. As we go from left to right, atomic radius goes down. As we go from top to bottom, atomic radius goes up. And here's an overall example, a picture of that. I'm assuming this picture may be in your book somewhere. The atoms here look a little bit ovular. Now, atoms aren't ovals, they're circles. But, you know, they're ovals in this case because I was trying to stretch the picture. So you can see here as we go from left to right, we certainly have a decrease in the size, the overall size of the atom. So from left to right, we are getting smaller. Big guy here, little guy there. As we're going from top to bottom, we are actually getting bigger. So let's do a little concept check. Which of these should be larger? Sodium or chlorine? And hopefully you pick sodium. Now, why should sodium be larger? Sodium should be larger because the electrons are not bound as tightly due to a smaller effective nuclear charge. Let's try another one. How about this? Which is larger, lithium or cesium? You should have picked cesium. Why is cesium larger? Because it is further down the periodic table. It has more energy levels. Okay, let's try another one. Let's actually look at specific electrons now. Which is in specific orbitals? Which is larger, the hydrogen 1s orbital or the lithium 1s orbital? Well, hopefully you thought of the hydrogen 1s orbital. It's larger because the lithium 1s orbital has 2 electrons in it. So there's 2 charges, and that's going to pull the 1s orbital closer to the nucleus. All right, let's move on. Oh, hey, one thing I want to speak of here that's not on my PowerPoint. So that was atomic radius. How about ion radius? Let's just quickly talk about this here. And let's just look at 2 different atoms. Let's look at sodium. And then let's look at sodium plus. All right, and let's think of what happens to the size of that particular atom as it loses its electron. So it's losing its outer energy level. Okay, so as sodium loses the electron, okay, let's take a look at its outer energy level. There's 1 electron here. So it loses that outer orbital. So your size for the sodium atom is big. Okay, for your sodium ion, it's going to be smaller. So let me make this guy a little bit smaller, okay? And the opposite is going to be true for a cation, right? So let's take chlorine, for example. Okay, chlorine is going to start out small, but then it's going to gain its electron, add an electron to it. Okay, and now it's going to get bigger.